exothermic and endothermic processes as well as reactions. We're going to be dealing more with the chemistry stuff as we go through, but we need to think about some of the processes like phase changes, because that's what we're most comfortable with and what we've seen the most examples of over the years. So when we have a reaction, for a reaction to occur, there has to be a collision between particles, and the collision has to be in a specific orientation. If it's not in a specific orientation, remember we're in 3 dimensions, and they're moving around. All particles are always moving around at least a little bit. They have to hit each other in the correct way for a reaction to occur. And you can go down to that link down there if you want to go ahead and take a look at a very brief 11-second video that kind of shows you how hydrogen and iodine would have to be in the correct orientation for the reaction to occur. Not only must the collision be in the correct orientation, but there must also be enough energy to break some bonds and make some new bonds. If there's not enough energy, a reaction will not occur. And this energy is what we're going to be dealing with in this new unit. And we're dealing with thermochemistry. So thermochemistry is the study of energy changes associated with chemical reactions. So if we take substance A and substance B and combine them, is there enough energy for them to react? And that's going to be an essence of what energy is in their bonds, what energy would be in the bonds of the new products, what energy do we put into the system, so do we have to add heat for a reaction to occur? We're going to look at all of those things. This thermochemistry is measured in joules, that energy change, measured in joules, which is a capital J. Sometimes you'll see a question that's written in kilojoules or asking for the answer in kilojoules, which would be a lowercase k and a capital J. Hopefully you remember that for every 1,000 joules, there's 1 kilojoule. Thermochemistry is unrelated to rate, which we're going to be dealing with more in a future chapter. Rate is the speed of a reaction. So we're not talking about how fast or how slow a reaction goes when we talk about thermochemistry. We're asking, is there enough energy for a reaction to occur or not? We use 2 common terms interchangeably in the real world. We use heat and temperature quite often interchangeably, but they're not actually defined the same way. So one of the key things you're going to want to make some flashcards on are these definitions of heat and temperature. So starting out with the one that we deal with most often, temperature is a measure of the motion of the particles in a substance. So how fast the particles are moving or how slow the particles are moving. When we have a fast-moving particle, we're going to have a higher temperature than when we have a slow-moving particle, which would be lower. So if you think of water, before you put it on the stove top in the pot, you can see that the particles are going to be moving slower. It's in the liquid phase. But as you heat it up, energy goes into the system and they start moving faster. Some of them turning into gases and escaping that pot. Well, then we've got our gas, which is a higher temperature because they're moving faster. Heat, on the other hand, is the flow of energy. So we're not measuring motion here. It's how energy flows due to a temperature difference. So if I'm holding my coffee mug with freshly poured coffee, my hands are initially a lower temperature because my particles are moving slower. The coffee has fast-moving particles, so if I were to measure the temperature, it would be much hotter, higher temperature than my hands are. Well, as I hold my coffee mug, I feel my hands start to get warmer. That is because energy is flowing from the coffee, the hot-moving, fast-moving particles. They're going to hit the particles on the mug and then on my hand as a result, and they're going to start moving faster. Well, with each collision that makes my hand particles move faster, the particles in the coffee are going to, as a result, move slower. So now if I were to measure temperature after I've done all of this heat, I will see that the temperature of the coffee is no longer as high as it was before because the particles are not moving as fast. But my hand particles are moving faster, so if I measure the temperature of that, they would be hotter than they were before. That is again because energy flowed from one spot to another. And it always goes from higher to lower. So my hands got hotter, not my hands gave energy or something to the coffee. It's the opposite direction. It's always going from hot to cold. Energy is flowing from high energy to low energy. We can also talk about enthalpy. That's another key word that you'll want a flashcard for. It's also known as heat content. The symbol we use for enthalpy is the capital H. We don't use E because E is generally used for energy. The definition of enthalpy is that it is the total energy of the system. So we think about a system, let's say it's my coffee mug again. The system is the coffee, where my coffee is. The surroundings, everything around it, would include my hands, the air, everything else in the room. Chemical potential energy, we know potential energy is energy that has the potential of being there, doing something, changing to kinetic energy. Chemical potential energy is energy that is stored within the bonds. So when I bond hydrogen and oxygen together, there's some energy there that we can then convert in various ways. When we deal with enthalpy change, we have the potential energy change when breaking or making bonds in a reaction. So that hydrogen-oxygen bond that I had before, maybe I split it up in a decomposition reaction to H2 and O2. Well, those new bonds are going to have a specific potential energy, and it's going to be different than what we had before. The symbol for enthalpy change, we know delta is what we always use for change. The change in enthalpy, delta H. And it is the difference between the reactants and the products. When we have an endothermic process, energy has to be absorbed into the system from the surroundings. It needs some energy for the reaction to occur, or for the process to occur. So heat is flowing into the system. So the ice pack I was using earlier today, it went from nice solid ice to liquid water because heat flowed from my hands into the system, into the ice, and it absorbed that energy and went from a solid to a liquid. So heat is flowing into the system. The reactants, so if we're now changing our minds from processes to actual reactions, the reactants are going to be more stable than the products. We often use an energy level diagram to discuss this. So we have energy increasing on the y-axis, time increasing on the x-axis. The reactants we see here are lower in energy, which means that they are more stable. The lower in energy, the more stable they are. The products have a higher energy and so are less stable. The energy absorbed is what we need to go from reactants to products in an endothermic reaction. And we deal with this as a delta H that is positive. So we'll often write it as positive delta H. And notice here we have an activation energy. So we don't have a nice straight line between the reactants and the products going up. We have some initial energy that has to be overcome for this reaction to take place, and that deals with that initial collision that we were talking about, what's required. Exothermic processes release energy. Heat flows out of the system, so that again would be my coffee mug if we're thinking about processes. If we're thinking about chemical reactions, well, that would be a good combustion reaction. If I light something on fire, it's going to be an exothermic process. The products are more stable than the reactants are. The energy level diagram. Energy again is increasing on the y-axis, time is increasing on the x-axis, and we see here that the reactants are higher in energy and therefore less stable than the products, which are lower in energy but more stable. Energy is released in this, so we would have a negative delta H. And even though we're going from less stable to more stable, we still have an activation energy to overcome. So it's never a straight line between those reactants and products. We always have to overcome that activation energy in some way. So the big idea here, the energy gained or lost by the surroundings has to be equal to the energy lost or gained by the system. This is like our conservation of mass. Same sort of thing going on here. The reason we balanced reactions, same thing is going on here. Energy is not suddenly disappearing. Maybe changing into a different, less usable form, but it's going somewhere and we can track that. If we're dealing with reversible reactions, the products and reactant energy content remains the same no matter which direction we're going. But so the magnitude of the delta H is going to be the same, so the change in enthalpy will always remain the same, but the sign's going to differ. So the exothermic would be negative, the endothermic would be positive. Let's say it's 10, it would be negative 10, and the other direction would be positive 10, or vice versa. Some different examples. Ice melts when you touch it. So ice is the system, the surroundings are you touching it. So your energy is being transferred into the ice, so it is endothermic. This one is redundant, it's the same thing. Ice cream melts, it's taking energy from the surroundings, endothermic. Propane burns in a propane torch. The propane would be the system, the surroundings would be everything else around it. It's releasing energy, it's going to feel hot in the area surrounding it, so exothermic. And then if I have two chemicals mixing in a beaker giving off heat, that means my beaker is my system, my chemicals in my beaker, I should say, are my system. Around it, or the surroundings, it's giving off heat. That's my clue there that it's exothermic.